Okay, this is third section in chapter 1 on interactions of waves. So far we've talked about what waves are, and then we talked about the properties like amplitude and wavelength and frequency and speed and all of that. So these are some things on how waves interact with each other. So the first one would be reflection. So reflection is when something hits a surface, it cannot pass through and it bounces back. We've talked about reflection before. But with with waves, I should say, this image is showing light waves because it's hitting off the girl's sunglasses, but with any sort of reflection in waves, the law of reflection is this. The angle of the incoming wave, which we call the angle of incidence, is equal to the angle of the reflected wave, which is the angle of reflection. So when it comes and hits off of something, it will, like showing this girl's, so they're showing with this girl, the angle coming in of the sun hitting her glasses, that angle is going to be equal to the angle of reflection, so the angle that's coming off of her glasses and being reflected off. So that's reflection of waves. When they come in, they reflect off of something, so they can't go through it, they bounce off of it. The angle that they come in is equal to the angle that they go off after being reflected. Okay, so this is refraction. This is the second way that waves will interact. And so this is basically, it's bending of waves due to a change in speed. So for instance, if you go from one medium to the next, so from air into water, or from, air into a liquid, or liquid into a solid or something, there's going to be a refraction or a bending of a wave. So one side of the wave changes speed for the other side because one side is entering in the medium while the other one is still out of the medium. So this would happen a lot that you might have noticed before if you're in a pool or something and you look down and it looks as though a toy is in a certain spot on the ground, it looks as though you dropped it on the ground and you go down to get it and it's not in the same space it looked like it was from above the water, and that's because of refraction. So you're looking at it from outside and is actually under the water, so the light waves have bent, making it look as if it's in a different spot than it is, if that makes sense. And same thing if you put like your arm underwater, it looks like it's kind of moved over a little bit, and it hasn't. That'd be the way that you've probably seen refraction firsthand before. You don't necessarily see, you can see that reflection, you can see how that light wave bends and makes it look slightly different because that speed has changed. So once it gets into the water, the wave speed slows down a little bit. The same thing if you're looking inside of an aquarium, same thing. So the light wave slows down a little bit when it hits the water, meaning that it's going to bend a little bit, means that your view is going to change a little bit. Okay, so this is diffraction. And this is so waves moving around a barrier, basically. So what they'll do is they'll come together and then they'll spread out again. So for instance, maybe there is a fire alarm ringing out in the hallway, and the waves need to get into the classroom. What they'll do is they'll come as they're kind of spreading out throughout the hallway, so everyone can hear them. They'll come to the door of each place, and it will they'll bend in a little bit to go through the door, and then they'll spread back out once they get through the door, or around a corner or something like that. Once they kind of hit around the corner, they'll spread out again and kind of fill that space. So if they get to some sort of barrier that they cannot pass through, but there's a space for them to get through, they'll kind of bend to get through that space and then spread out again once they've gone through the area that contains the barrier. So it's going on here with the waves that are coming into shore, the waves that are going through like an area that has kind of a small opening. The waves are coming through, and then they're bending out again once they get through that small opening. Or if they're going around a barrier, they're going to spread out again once they go around that barrier. Alright, so next we have constructive and destructive interference. So if they're constructive, that are going to make a larger amplitude. If they're destructive, that are going to make a smaller amplitude. So when two waves meet, if they meet in a point where both their crests are in the same spot, they're going to make a much larger amplitude. Whereas if they meet where their crest and their trough kind of are the same spot where they meet, then it's going to basically equal itself out. They can either be constructive, build each other up, or destructive, kind of cancel each other out. So they're going to have a smaller amplitude if they're destructive. They're going to have a larger amplitude if they are constructive. And that's when they just basically two waves meet. They're coming from two different directions. Okay, so this would be a type of interference. In this case, we could create what we call a standing wave. This appears to be a wave that's standing in place. So there's points of zero amplitude, which means basically they've kind of stopped moving. So when they go through each other, they create areas of zero amplitude. And so we have these things called nodes and antinodes. Antinodes is the area of more energy, whereas nodes is the area of very low energy. That's kind of where the two cross each other. So again, these are basically interfering with each other, creating a place where the wave appears to stand still. The nodes are going to be evenly spaced, and they're points of zero amplitude on what we call a standing wave. So then antinodes are also going to be evenly spaced, and they're the points of maximum amplitude. So it seems weird because usually you would think antinodes would be like no amplitude, but in this case antinodes are actually the part where the amplitude is the biggest. Resonance actually happens to be kind of the most interesting, I think, of all of the types of interference. Everything has a natural vibration to it. If their amplitude of vibration gets so big that it matches the natural amplitude of something, or the natural vibration of something, it can cause that frequency. It can cause such a large frequency, it can cause breakage. So if you've ever seen someone break something glass, like you've seen a YouTube video or something where someone's broken a glass with their, like singing a certain note, bridges have come down this way. Usually this is the point where I'd show you there is a bridge, and I think Tacoma, Washington, was a long time ago. But there's a bridge there that actually the wind one day matched the natural frequency of the bridge itself, causing the bridge to kind of ripple in place. If you want to look that up on YouTube, I believe it's Tacoma, Washington. Put bridge, Tacoma, Washington. You should be able to find a film of that. It's pretty cool how the bridge kind of just goes back and forth and up and down along with the wind itself, because, again, the wind matched the natural frequency of the bridge. They take very good care not to have that happen anymore. In fact, if like marching, I don't know if this is mentioned in the book, but it was mentioned in books before that we've read, that a lot of times soldiers will break step, like they won't march at the same beat that they go over a bridge to make sure that they don't match the bridge's natural frequency. But again, there's lots of different examples of resonance out there. That's what this whole overall term is resonance. You could even put resonance and bridge to Tacoma, Washington. That might help too. Anyway, but it's kind of cool to look that up. So if you ever want to see like resonance in action, put that in something into YouTube. Just put resonance, and maybe you can find something, someone breaking the glass with their voice, whatever. But you have to figure out what that natural frequency is, and then you have to match it. And if you match it, you put enough vibrations into something, you can basically cause those things to break. All right, so this is the end of section 3 on interactions of waves. This should be in your packet. If you pick it up at school, or you can print it off from PowerSchool Learning, or you can just do it on a separate sheet of paper, take a picture when you're done, hand it in, however you want to do that. You can either upload it to PowerSchool Learning in the inbox, or you can send it to me via email. Lots of different ways you can hand these in. All right, enjoy!